Previously, we have used the correlation coefficient to describe the relationship between two continuous variables. However, the correlation coefficient has two drawbacks. First of all, it only works for a linear association between the variables. Secondly, it only gives an indication about the strength and not the model. So if we also want to have information about the model describing this relationship, we can look at regression. Regression is a statistical method which has the goal to describe the relationship between two series of observations, xi and yi. So what we want to do is we want to find a model which explains yi in function of x. Yi is called then the dependent variable, the outcome or the response variable. X is called the independent variable, explanatory variable or the predictor. In the example that we will be using, we will try to predict the basal area of coarse woody debris by looking at the tree density. So the basal area of coarse woody debris is the area in a forest which is covered with dead trees or dead trunks. So we measured for 16 locations, 16 North American lakes. We measured on the one hand the tree density, which will become our variable x, and we also measured the basal area, which is then the outcome variable y. At first, it's always good to make a scatter plot. Why? Because a scatter plot shows us the data and it gives us an information about the relationship between them. If we want to see what happens, or if we want to get an idea about the relationship, we can add a smoother line. So this is the dotted line on the plot, which is a prediction for the relation between x and y. We see that the smoother is almost linear, and so a linear regression line, adding a linear regression line seems plausible. So what we also noted was that if x is fixed, so for the same value of x, the outcome variable y is not always the same. So our observation, our y, will be a signal part, so it will be a function of x plus some noise due to variability. If we want to write it in a mathematical sense, we will write that yi equals f of xi plus epsilon I. So on the one hand, we have the observation yi equals the prediction by the model plus some error term. The prediction will also be noted as yi hat. So we want to find f, and if we know nothing about f, the best that we can do is take the average. So if we look at all values x, so we want to find f of x here, this x, we will look at all the outcomes y for which that the input variable equals small x. And now we take the average of those. So we get a conditional average of yi, a conditional average of the observations, which will give us the prediction f. Because we took this average, it also means that on average, here, the average of the error terms becomes 0. What we then do is we often make an assumption on f. For linear regression, the assumption is that f is a line or a linear function. Why a linear function? Because it's a very easy function and it has nice interpretations. So it means that this one, so the f of x, the average, equals alpha plus beta x. Alpha and beta, the slope and the intercept, are unknown, and so we'll have to estimate these using the data, which gives us an alpha hat value and a beta hat value. Of course, we made the assumption of linearity, which we will then also have to verify later on. However, if this assumption holds, we get an efficient method. Why do we call it efficient? Because we use all the observations and not just ones x equal to small x. So what we will see in the formula of alpha and beta, we will see that we do not only use x equal to small x, but we use the entire data set to get an idea about alpha and beta. There are two uses for linear regression. The first one is prediction, the second one is association. So a prediction is very easy. If we know x, we know a value for the input, we can make a prediction for the output by just plugging it into the model. So in the model, once we have determined alpha and beta, so we made the predictions for alpha and beta, we just plug in the value x, and here this gives you an actual value for the prediction. The second way we can use linear regression is to get an idea about the association between x and y. So what we mean here is what happens to y on average. So this is important because we have here always the expected value. It's what happens to y on average if my value of x changes with a certain number. So in this case, with delta. So if we plug it in, we see that for the first one we get alpha plus beta x plus delta, and then minus alpha minus beta x. So in the end, if beta changes with, if x changes with delta, on average y changes with beta delta. So the change in the outcome is proportional to the change in the income, which also gives us the interpretation of the slope, beta. The slope is the difference in the mean outcome between subjects that differ 1 unit in the value of x.